in order to demonstrate how a capacitor stores charge, we built a water bottle capacitor which uses a steel nail through a bottle cap, tin foil wrapped around the edges of a water bottle, and salt water, warm salt water, to increase the electron permittivity and the dielectric constant. Sorry, not to increase the electron permittivity, but to increase the dielectric constant. And so to do this, we will pour the warm salt water into the capacitor.
Capacitance is defined as the amount of charge held at a certain voltage. This means that the capacitance is relatively equal to the total amount of charge on a plate divided by the electric potential of the circuit or system. However, in reality, a capacitor is defined more by its geometry than by its energy storage. The formula shown on the blackboard is C equals kappa times the electron permittivity, or the vacuum permittivity, times the area of a plate divided by the distance between the plates. This means that as the dielectric constant increases, then the capacitance will increase. As the area increases, the capacitance will increase, but as the distance increases, the capacitance will decrease because the dielectric constant and the area is directly proportional to the capacitance, while the distance is inversely proportional to the capacitance.
So right now, Scythe will screw the nail into the water, which will allow for a charge to pass between the tinfoil plates and the nail. And then we will use a multimeter to measure the capacitance. Left, too. So we've designed an experiment to test the capacitance of several capacitors in series. So just to make sure we're not jinxing you, we will test the capacitance of each one separately and then see how that affects the capacitance of them in series. So the first one has a capacitance of relatively 0.3 nanofarads. The second one has a relative capacitance of 0.28 nanofarads. The third one has a relative capacitance of 0.30 nanofarads. And the fourth one has a relative capacitance of 0.28 nanofarads. So they're all relatively the same capacitance. We all agree on that? Perfect. So now we will see if this one has, number of capacitors, and so the capacitance in farads. So let's just say that the capacitance is 0.29 because that would be the average of all of them. So now that we have the capacitance of each separate capacitor, we can see how they act in series and in parallel. So we will begin with in series. So we will measure from the input to the output of the second one. So we will go from here to here. And that gives us a reading of 0.17 nanofarads. Sorry. That's not good looking. Sorry, erase. So now that we have two, we've got to connect it to the third. You can tape that on there. So we go input to output again. we get 0.14. And then finally, we'll go input to output one last time. Oh shoot, that's not good. We'll go A to B. And we get 0.09 nanofarads. Okay. So, using this knowledge, they seem to be going down proportionally. So then we can say that the first one goes down relatively a half. And then the second one, it doesn't go down perfectly a third, but we can relatively say that went down a third because we cannot measure perfectly for the capacitance. And this last one should go down relatively a fourth because our equation is so we already demonstrated the capacitance of the capacitors in a series. So now we're going to see how the capacitors act in parallel, and we do this by taping the tops to each other rather than flipping them over each time like we did in series. A little note, the capacitance seems to have gone down for each capacitor because when we were taking it off, we ripped the capacitors, the majority of them, at some point. So the majority of the capacitors are around 0.24, 0.25 now. So we're going to measure the input and the output of 2 because we can just assume the capacitance is 0.24. And I guess this is a capacitance of 0.52. Let's go to the next one. Make this so I can tape it on there like that. Tape this onto the bottom. We'll hold that right there. So 0.67. And then we'll go to our last one. Which has them taped at. .82. Yeah. Okay. So then with this knowledge, the capacitance increased each time. So the first time it was increasing by 2, and this is supposed to have increased by 3 and then 4. And we know that because, we've done more other experiments, but the most likely reason is that the capacitance was just lost through either shoddy connections or because we're using this through a glass table that's not really going to make it work. So we know the capacitance equation is the summation of the number of capacitors, and that's basically how it works, summation of all the capacitance. Okay, so what we have here is an RC circuit, otherwise known as a resistor capacitor circuit, and we use this using the FET simulation, our sponsors, JK, they're not our sponsors, but we built this circuit on the FET simulation because of the dangers and difficulties of building one in real life. And so I will charge this circuit, and because the capacitor and the resistor, the light bulb, are in series. So when I first close the switch, pay attention to how the light bulb lights up. So as you can see, the light bulb slowly grew dimmer. Now let's just remember that fact as we watch and pay attention to how the plates charge. Now I'll close the capacitor, the switch. And then as the plates charge, the light bulb seemed to grow more dimmer. Or dimmer, sorry, not more dimmer. And so then lastly, I'll do this one more time and pay attention to the current graph over here.
Front door.
So as you can see, the graph of the current slowly got lower and lower. And this is because as the current flows from the battery, the power source, through through the circuit, it lights up the light bulb. However, this current gets to this capacitor, and the capacitor charges. And as the capacitor charges, the current slows down because there's a greater resistance acting to keep charge from flowing. So as the current slows, the light bulb also gets dimmer. And this is how the resistor and capacitor act in a series together. So here we have another RC circuit, resistor capacitor circuit, but this time we connected the capacitor and the light bulb in parallel. And so this time we'll see how the current and the brightness of the bulb and the charge on the capacitors interact. So the first time when I charge when I close the switch, watch how the light bulb charges. Or lights up, sorry. So the light bulb gradually grew brighter rather than dimmer. So now I'm going to open the switch and we're going to continue to see what happens. So now everything seems to be back to equilibrium relatively. There's no current running through the circuit. So now watch how the charge on the capacitor works together, just how it works. Circuit. Closed circuit. Now I'm going to open the switch. And then lastly, let's watch how the current on the graph operates. So we're going to close the switch. See our peak, gradual fall, but then it levels off at 0.5 amps. So now then let's open this circuit back up. Oh shoot. And it returns to 0. However, that current is only running through this switch and through these wires. So now let's go down here and let's see how the current interacts. So now let's close the switch. And we see a gradual climb this time to 0.5 amps. And then it levels off. And then when we open the switch, we see a gradual decline to 0 amps. So now then we have to make sense of how this all works together. So what happens here is when you close the switch, since you have basically, we'll just say 2 places that the current could go through at this junction, the current is going to initially take the one that has the least resistance, which is the capacitor, because it has relatively 0 resistance whenever there's no charge on it. However, as more charge accumulates on the plates of the capacitor, then the current will gradually shift over to flowing through the light bulb, and that is why the light bulb gradually grows brighter. Then, whenever we open the switch back up, the capacitor is going to discharge in the opposite direction, causing the current to flow through the little circuit and briefly light up the light bulb. Not as bright, however. Okay, so now here's the thing. Y'all, I've given y'all this like 12-minute video or 14-minute video on what a capacitor is, how it acts, and all this stuff. But really, why do we use a capacitor? So first off, we're going to go into a little demonstration here. Now, imagine this as your long wire, and this is your parallel plate capacitor. Now, these are electrons moving through the circuit, and I am the battery. So we're going to put this battery right here, and we're just going to push more charges, slowly but surely, onto the parallel plate capacitor. Until, guess what? Until slowly but surely, there is no way to fit more charges onto that capacitor. And so when this happens, the capacitor is considered charged. And so this was basically a demonstration of how the capacitor charges itself. But it also gives us a very insightful look at what happens. because this is just charge on the capacitor. And so it signals, what would we use a capacitor for? Well, we'd use it to give off high amounts of charge, or not necessarily high amounts of charge, but time whenever you have to either do a timed power outlet or a high amount of power. So this would be used in clocks, whenever the wheel ticks, because the energy would store in the capacitor, and then the arrows, I guess, would point moving at the numbers. This would also be used in cameras for the flash. Oh, whoops. And then lastly, and most importantly, this would be used in a little instrument I like to call the theremin. And I mean, I'll face it towards you so you can see. But how the theremin works is this is basically one parallel plate, my hand is the other. And even though this is not necessarily how the traditional use of a capacitor, we're still using a capacitor. I have a question here that is demonstrated to demonstrate two properties, well, multiple properties of capacitance, basically supposed to sum up the whole video. So first off, we're asked to find the energy stored, and then secondly, we're asked to find how long to charge. Now, how long to charge is not necessarily in our curriculum, but it is something I think we should be aware of. So first off, we'll start off with how to find the energy stored. So first off, we have to find the capacitance. That's the number one thing we need to do. So the capacitance, like we already said, is equal to kappa epsilon naught times the area divided by the distance. So in this circuit, it's all given to us. So all we have to do is plug it in. So what is the dielectric constant? 1.2. What is the electron permittivity? 8.85 times 10 to the negative 12th. And then area, 10 meters. And then the distance of separation, 5 centimeters. So when it's 5 centimeters, that means 0.05. So this number is equal to 2.124 times 10 to the negative 9. Sorry, I'm not doing sig figs. So now then, though, we need to find the energy stored. So how do we do that? Well, this is a very important concept. We need to know there's three ways to find the energy of the capacitor. The energy of the capacitor is equal to 1/2 Q delta V. It's also equal to 1/2 the capacitance times the change times the potential difference scored. And then lastly, it's equal to 1/2 Q squared over C. Now, with this knowledge, we can find the energy stored. So we really have three equations to choose from here. Now then, though, since we just found the capacitance and the voltage of the circuit is given to us, then I don't see why we just don't do the easiest equation. Sorry, Mrs. Fincher. So C times the potential difference squared. So let's plug in our variables. Our C was given to us up here, 2.124 times 10 to the negative 9 times the change in the potential difference, which is 9 squared. And so then let's do that, which gives us 8.602 times 10 to the negative 8th. And that would be our energy stored in joules. Lastly, we need to figure out how long to charge the capacitor. And this is given by an equation that I know we don't need to know, but I think it is necessary that we know it. And this is called the tau, the Greek symbol tau, is equal to the resistance of the circuit times the capacitance. And it is really that simple. What we take is the resistance, which is 3 ohms. We multiply it by the capacitance, which is 2.124 times 10 to the negative 9th. And that gives us 6.3